August 1998, North Atlantic Ocean. A commercial fishing vessel runs its standard route, nets deployed, crew expecting the usual haul. But for 3 consecutive days, the catch volumes collapse, and something else happens that the captain decides to write down. The ocean goes quiet. No whale calls. No fish vocalizations. No ambient biological noise at all. Just the hum of the engine and the sound of empty water. So why did a sea full of life suddenly produce nothing, not a single recordable sound, for 72 hours straight? Local marine logs from that same week confirmed the account. Nobody had an explanation. That silence would not be understood for 25 years, and what scientists finally found was stranger than anyone expected. Most people think of the ocean as a quiet place. It is the opposite. The ocean is one of the loudest environments on Earth, a continuous, layered biological symphony running 24 hours a day, across every depth, in every season. Whales produce calls that travel thousands of kilometres. Fish click and grunt during spawning. Shrimp colonies generate a crackling static loud enough to interfere with naval sonar. Even krill, creatures smaller than your thumb, contribute to the acoustic texture of the deep. Sound moves through seawater roughly 4 times faster than it moves through air, and marine life has evolved over hundreds of millions of years to depend on that fact. Navigation, mating, feeding, predator avoidance, all of it runs on sound. Hydrophones anchored to the seafloor can detect biological sound signatures from hundreds of kilometres away, which means scientists don't always need to see what's happening in the ocean. They can listen for it. And that is exactly what makes August 1998 so unsettling. A silent ocean is not peaceful. It is not serene. It is a diagnostic alarm. It means something in the food web has failed, at a scale large enough to shut down the entire acoustic environment at once. I'm your host, and what you're about to hear is the story of how one fisherman's log entry, ignored for decades, turned out to be the earliest recorded signal of a biological collapse that scientists are still working to fully understand. How it started, what it destroyed, and why the data collected since then raises a question nobody has cleanly answered yet. The sea went silent in 1998. The reason why changes everything we thought we knew about ocean health. It was 1998, and a weathered commercial fisherman was hauling nets somewhere in the grey chop of the North Atlantic, about 60 nautical miles off the Norwegian shelf. In a stretch of water he had worked for nearly 3 decades. His name never made it into the papers. The maritime records that hold his account list him only by vessel registration and licence number. The way those documents always do, bureaucratic and bloodless, stripping the humanity out of what is, in his case, a genuinely remarkable story. But the account itself is there. Logged in his own hand, filed with the relevant maritime authority, and then placed in an archive where it would sit untouched for 25 years. What he described was this. He had been fishing the same corridor of water since the early 1970s. He knew its rhythms, the way you know a road you drive every morning. The seasonal shifts in current, the way the thermocline dropped in late autumn, the particular quality of the surface chop when a northwest wind had been running for more than 2 days. He knew where the fish should be, and when, and roughly how many. That knowledge was not mystical. It was accumulated observation, logged carefully over decades, the kind of empirical record that serious commercial fishermen keep because their livelihood depends on getting it right. In the summer of 1998, the fish were not where they should have been. That alone was not alarming. Fish move, stocks shift. Any experienced fisherman will tell you that the sea has always been unpredictable in the short term, even when it is reliable over years. But what unsettled him was not the absence of catch. It was the absence of sound. The North Atlantic, at depth, is never truly quiet. Beneath the surface noise of wind and wave, beneath the mechanical drone of the vessel's own engine, there is a constant, layered biological hum. Shrimp populations produce a faint crackling that experienced fishermen can sometimes detect through the hull. Schools of fish create low-frequency pressure shifts. Marine mammals, minke whales, dolphins, the occasional fin whale passing through, add their own acoustic signatures to the water column. The sea, in other words, talks. It has always talked. Fishermen who work the same waters long enough learn to read that conversation even without instruments. In the summer of 1998, the conversation stopped. He described it in his log as fishing in a dead sea. Not a rough sea, not an empty sea in the ordinary sense, but a sea that felt acoustically hollowed out. The hydrophone equipment on his vessel, basic by research standards but functional, registered almost nothing. The usual biological noise floor had dropped to something close to silence. He wrote that it reminded him of a forest after a fire. The structure was still there, the water still moved, the sky was still the same sky, but something essential had been removed from the interior of the place. His catch volumes that summer collapsed to roughly 30% of his 10-year average. That was not a bad season. That was a statistical alarm. Over the following 3 months, he filed formal catch reports that documented the decline in precise numbers, tonnage by species, by week, by location. The herring were almost entirely absent from his usual grounds. The cod, already under pressure from years of overfishing, had retreated to depths and positions that made no seasonal sense. Even the seabirds that normally work the surface above productive feeding zones were sparse. The whole food web, from his vantage point on the water, appeared to have shifted or withdrawn. Maritime authorities received his reports. They noted them. They did not have the tools, the funding, or frankly, the framework to investigate what a single fisherman's log could not on its own prove. A collapse in one vessel's catch could mean a dozen things: equipment issues, navigation error, bad luck, the ordinary variance of a complex system. Without corroborating biological survey data from the same zone and the same window, there was no mechanism to escalate the report into anything resembling a formal inquiry. So the log was filed, and the archive closed around it. What makes his account extraordinary is not the silence he described. It is the precision with which he described it, and the fact that he was right. 25 years later, when researchers began cross-referencing historical maritime records with long-term hydrophone data and retrospective biological surveys, his log would turn out to be one of the earliest documented human observations of a biological event that was, at the time, completely invisible to science. He had no satellite data. He had no peer-reviewed framework for what he was experiencing. He had 30 years of accumulated knowledge about a specific body of water, and he used it to notice that something had gone catastrophically wrong. That was only round one. Because what he could not have known, sitting in that wheelhouse in the grey summer of 1998, writing in careful longhand about a sea that had gone quiet, was that the silence was not random. It was not a temporary fluctuation. It was the surface expression of something happening far below the reach of his nets, in the pressure and chemistry of the water column itself, something that had begun weeks or months before he noticed it, and that would continue long after his season ended. Maritime authorities would look back on this moment and wish they'd made a different call. Not because they were negligent, exactly. The system they were operating within simply had no category for what his log described. There was no protocol that connected a fisherman's acoustic observations to geological monitoring, or to the kind of deep water chemistry data that might have explained what he was hearing, or rather, failing to hear. The dots existed. Nobody had drawn the lines between them yet. For a while, things actually seemed fine. The following winter brought slightly improved catch reports from adjacent zones, and the Maritime Office closed the file on the 1998 anomaly without further action. That didn't last. Picture the seafloor of the North Atlantic in the early months of 1998. Not the surface, not the grey chop and the fishing vessels and the seasonal light, but the bottom, where the water pressure runs to hundreds of atmospheres and the temperature hovers just above freezing, and the darkness is absolute and complete. Down there, the geological processes that built the ocean basin in the first place have never stopped. The Mid-Atlantic Ridge, running roughly north to south like a seam down the centre of the ocean, is one of the most seismically active structures on the planet. It moves, it breathes, it shifts in ways that are slow by human timescales, but violent in terms of energy release. In 1998, it did something significant. Between February and October of that year, a seismic swarm, not a single earthquake, but a prolonged sequence of hundreds of smaller events, moved through a section of the North Atlantic Basin that overlapped almost precisely with the zone where the Fisherman had been working his nets. Geological monitoring stations, the kind operated by universities and national survey agencies to track tectonic activity, recorded the swarm in detail. The data was logged, analysed for its geological significance, and filed. It was not at the time connected to anything biological. Why would it be? Seismology and marine biology were separate disciplines operating in separate institutional worlds, looking at the same body of water through entirely different lenses. But the swarm left marks on the ocean that went far beyond the shaking of the seafloor. Seismic activity at that scale and duration does several things to the water column above it, and none of them are gentle. The pressure waves generated by repeated seismic events propagate upward through the water with enough force to disorient or physically stress organisms that depend on pressure sensitivity for navigation, which, in the ocean, is most of them. Whales, dolphins, and fish all use pressure and sound for orientation, communication, and prey detection. A sustained seismic swarm is, from their perspective, something like living inside a building where the walls are constantly, unpredictably shuddering. The instinct for mobile species is to leave, and they did. Marine survey data from adjacent zones, collected for entirely unrelated purposes in 1998 and 1999, shows anomalous congregation of normally dispersed species in areas well outside their typical ranges. Minke whale sightings shifted northward. Several fish species appeared in unusually high densities in zones that were not their preferred habitat. At the time, these observations were recorded as curiosities, statistical outliers, possibly explained by prey movement or temperature anomaly. Nobody was looking for a seismic explanation. Nobody was looking across the data sets at all. The chemistry of the water was changing too. That's not a typo, by the way. Seismic activity along the ridge was releasing dissolved gases and mineral compounds from the seafloor sediment, a process that measurably altered the local pH of the water column in the affected zone. Small shifts in ocean pH, even fractions of a unit, can have disproportionate effects on organisms with calcium-based structures. Zooplankton, shellfish larvae, the microscopic architecture of the food web's foundation. A pH shift of 0.1 units might sound trivial. In a biological system calibrated over millions of years to operate within a narrow chemical range, it is not trivial at all. It is the difference between a system that functions and a system that begins, quietly and invisibly, to fail. The sediment disruption compounded everything. Seismic swarms of this duration disturbed the benthic layer, the thin, biologically rich zone where the seafloor meets the water. Nutrient cycling that depends on stable sediment chemistry was interrupted. Microorganisms that form the base of the deep water food chain were displaced or killed in localized patches. The disruption did not announce itself. There was no visible sign at the surface. The water looked exactly the same. The sky looked exactly the same. But beneath the thermocline, in the cold, dark water, where the real architecture of ocean productivity is built, something had been knocked sideways. A seismic swarm of this duration and intensity in a biologically productive zone was a warning sign. The geological monitoring agencies ignored it, not out of carelessness, but because the framework for connecting seismic events to biological outcomes simply did not exist in any formal, operational sense in 1998. The two catastrophic processes, the geological and the biological, were unfolding in the same water at the same time, and they were completely invisible to each other in the data. Two separate monitoring systems, both functioning correctly, both recording real events, neither one aware that the other's records told the second half of the same story. If that sounds bad, keep watching, because the biological consequences of what happened in that water column in 1998 were not immediate. They were delayed. They worked their way up through the food web slowly, one trophic level at a time, in a cascade that would take years to fully express itself and decades to be recognised for what it was. The fisherman noticed the silence first because he was closest to the water and had the longest baseline of comparison. The geological monitors recorded the mechanism. But the full damage, the true scale of what the seismic swarm had set in motion, was happening at a level that neither the fishermen nor the geologists were equipped to see. The North Atlantic's smallest creatures had roughly one season before the disruption reached them in force, and the clock had already started. Picture a single cubic metre of North Atlantic water in late spring. Not the surface. Go down about 40 metres into the cold layer where the light still reaches, but the temperature drops sharply. In that 1 cubic metre, on a healthy day, you might find several thousand individual krill. Euphausia superba's cold water cousins, small translucent creatures no longer than your thumbnail, each one pulsing through the water column in slow, rhythmic bursts. They are not dramatic. They do not breach or sing. But multiply that cubic metre across hundreds of kilometres of productive shelf water, and what you have is the acoustic and nutritional engine of everything that lives above them. Krill click, that is not a metaphor. The mechanical action of their feeding appendages, their molting, their mass movement through the water, all of it produces sound. Biological sound. The kind that fills a hydrophone recording with a low, constant texture, like static from a living thing. When researchers describe the North Atlantic as a loud ocean, they are partly describing this. The krill layer is the baseline hum beneath every whale call and every fish chorus. It is the foundation on which the entire acoustic structure of the food web rests. By the late 1990s, that foundation was already under stress. Sea surface temperatures in the North Atlantic had been climbing incrementally through the decade, and the consequences were working their way downward. Warm water holds less dissolved oxygen than cold water. This is basic chemistry, the kind taught in introductory oceanography courses, and it has consequences that scale enormously when applied to an entire regional ecosystem. As the warmer surface layer deepened and the cold upwelling that normally refreshed the midwater column was suppressed, oxygen levels in certain depth bands began to fall. Not catastrophically at first, gradually, then faster. The seismic swarm changed the timeline. When the seafloor fractures along a fault system, it does not just shake the water above it, it disrupts the thermal layering of the water column. Cold water that would ordinarily rise from depth, carrying oxygen, carrying nutrients, gets deflected. The upwelling that had been quietly maintaining livable conditions in the mid-water zone was interrupted across a localised but critical stretch of shelf. Within weeks, not years, the oxygen depletion in that zone crossed a threshold. The real question is what happened behind closed doors, or rather, what happened in the dark, in that oxygen-depleted band of water, where the krill had nowhere left to go. Krill cannot outswim a dead zone. They are not fast enough, and the zone, in this case, expanded faster than their dispersal rate. What the data from subsequent trawl surveys showed, surveys conducted in 1999 and again in 2001, was a population crash that was localised but severe. In the affected zone, krill biomass had fallen by an estimated 70 to 80%, compared to baseline readings from the early 1990s. To translate that into plain terms, Roughly 4 out of every 5 krill in that region were gone. That is not a dip, that is a collapse. Now, the food web above the krill could have stopped there. It didn't. The collapse propagated upward with a speed and completeness that the available monitoring infrastructure simply was not designed to capture in real time. Sandlance and caplin, the small forage fish that feed almost exclusively on krill during their juvenile stages, began showing up in trawl surveys with empty stomachs and stunted growth profiles. The fish that fed on those fish followed suit. And the whales, the great baleen whales that filter krill and small fish from the water in volumes that seem almost impossible, began to leave. Not all at once, not visibly to anyone watching from shore. But the acoustic record, which we will come to, tells a story of departure that is almost orderly in its progression. The large biological sound signatures, the low-frequency calls of fin whales and the complex vocalizations of humpbacks begin to thin in the hydrophone data from 1998 onward. By 2001, they are sparse. By 2003, they are, for all practical purposes, absent from that stretch of shelf water. What remained was vessel noise, engine harmonics, the mechanical signature of human activity in an ocean that had stopped answering back. There is something worth sitting with here. The krill did not make headlines. There was no single moment, no dramatic image, no stranded animal on a beach that concentrated public or scientific attention on what was happening in the mid-water column off that stretch of coast. The collapse happened in the dark, at depth, among creatures that most people have never thought about and could not identify in a photograph. And yet the silence that followed, the silence that a fisherman noticed from the deck of his boat, the silence that would eventually show up in 25 years of archived hydrophone recordings, that silence began here, with them, with creatures the size of a paperclip vanishing from a cubic metre of cold Atlantic water, multiplied across hundreds of kilometres of sea. The oxygen depletion zones that formed in 1998 were not permanent. Within 2 to 3 years, as the seismic activity subsided and thermal layering partially restabilised, oxygen levels in the affected band began to recover. The dead zone, in the strict physical sense, healed. But the krill population does not simply rebound when the water chemistry improves. Recovery requires breeding cycles, larval survival rates, the re-establishment of the density gradients that make krill aggregation self-sustaining. That process, under favourable conditions, takes years. Under conditions of continued thermal stress, and the late 1990s and early 2000s were not favourable, it takes longer. The ecosystem had built its entire acoustic and nutritional architecture on the assumption that the krill would be there. Everything the food web had built was about to work against them. There is a server room somewhere in a NOAA facility that holds, on drives that have been migrated and copied and migrated again over the decades, the hydrophone recordings from that stretch of North Atlantic shelf. Thousands of hours of them. Year after year, from 1998 onward. Researchers who have listened to those files describe the same thing. Vessel noise. The low mechanical groan of distant shipping traffic, occasional engine signatures from fishing boats passing through. The equipment was clearly working. The data was being captured. But the biological layer, the krill texture, the fish choruses that used to build in the evening hours, the long low calls of whales moving through, was not there, not reduced, not diminished, absent. For years, those recordings sat in the archive without receiving the kind of sustained analytical attention that might have surfaced what they contained. Competing research priorities, limited funding for retrospective acoustic analysis, the sheer volume of data collected across all NOAA monitoring arrays. The silence was real, but no one had yet sat down to measure the full shape of it, to count the years, to lay the recordings end to end, and watch the flat line extend. It was only in the early 2020s that faint biological signatures began to reappear in the data. Small at first, uncertain. The kind of signal that an analyst might flag and then second guess. But they were there. Something had come back quietly to a place that had been acoustically empty for the better part of a generation. Think back to that morning on the water, a fisherman cutting his engine, listening. The surface flat and still and wrong in a way he could not yet name. He was hearing the end of something, though he did not know it. What the hydrophone archives tell us is that he was also, without knowing it, standing at the beginning of a very long silence. The ocean did not go quiet because nothing was left. It went quiet because the thing that knew how to fill it had been taken away. And for 25 years, the water simply waited. Dr. Elena Vargas listened again, and what changed permanently because of this story is that one fisherman's quiet observation finally became science. Subscribe for more comeback stories like this one.